Okay, we had started our discussion of the wavelet transform, just gave some brief motivation of why wavelet transforms are needed and some of their good properties. Today we will start talking formally about continuous wavelet transform. So the continuous wavelet transform is described primarily through a single function, which is called the mother wavelet. So the idea is to uh, it uses a single function, which we will call psi of t, that is localized in both time and frequency. So it's called a wavelet, let being small like the droplet, in the sense that it is localized in time. It doesn't go from minus infinity to infinity. Okay. And at the same time, it is also localized in frequency. So if you, for example, think about the short time Fourier transform example, we multiply our equation the way it goes. We have this function, even if it's a discrete function, the general principle stays the same. We are multiplying that with a wn times e to the minus j lambda m. So this wm is sort of a localized in time function. Right? It's a short window, but we don't pay that much attention as to how much localized it is in frequency. So in wavelet, the key idea is you start with a single function, this psi of t, which is called the mother wavelet. Okay. And it's called the mother wavelet because all the functions that we will use in this wavelet will be derived from this. Okay. So one example of this mother wavelet is what's known as the Haar wavelet. So wavelets are given names based upon their shape of this mother wavelet. Okay. So one wavelet goes like this. Okay. This is called the Haar wavelet. It goes from -1/2 to 1/2. Its height is 1 and -1. This is the Haar wavelet. Okay. Or when people say Haar wavelet transform, it means that the mother wavelet corresponds to this function. This is an example of a Mexican hat wavelet. It's called Mexican hat because it looks like, if you try to visualize it, it looks like a Mexican hat. So this is psi of t. Okay. Again, you can see it's localized. It goes to 0 after a while, so this is time. And if you compute the Fourier transform of this wavelet, that is also localized. Okay. It goes to 0. One of the most famous examples of wavelets are called Dobashi's wavelets, which is just a way of generating a sequence of Dobashi's wavelets. So they are called like Dobashi's 4, Dobashi's 8, and so forth. Okay. But the main idea is wavelet, you are beginning with it, you have a mother wavelet psi of t, which is both localized in time. Localized means it has a small time support, and it is localized in frequency. Okay? It has some frequency support. And the idea is in wavelet that you basically take this mother wavelet and you compute different shifts, time shifts, and number two scales of your wavelet, mother wavelet, to give you a collection of functions which will then help you encode your signal. Okay. At some level, I want to say that all possible time shifts and scalings of this mother wavelet give you perhaps a redundant representation, a redundant basis of the signal class that you are dealing with. Okay. So if we were dealing with orthogonal wavelets, which do exist, in that case we will just say that time shifts and scales of your mother wavelet essentially generate the basis of the function class you are dealing with. Okay. So let's start with formally what will make a mother wavelet a valid wavelet to be used in wavelet transform. And our focus here will be that we are interested in computing in analyzing signals x of t which belong to L2 of R. Okay? So all finite energy signals. So if we are talking about wavelet transform, we must be able to have either redundant representation or some basis which will be able to represent any function, any signal that is finite energy. So in the case of, for example, Fourier transform, these representations are given through the use of these complex exponential functions or sinusoids. Right? So in wavelets, instead of using complex exponentials or sinusoids, we want to use a mother wavelet. And what is a mother wavelet? It has to satisfy certain properties. Of course, it has to be finite energy. So it belongs to L2R. So the first property of mother wavelet is that it has mean zero. Its average is zero. So you take the integral of your mother wavelet and you end up with zero. So as much mass lives above zero as it lives below zero. Okay. That's the first requirement. The second is the usual requirement that we put on any basically basis function, which is that will work with unit energy wavelet, mother wavelet. So the L2 norm of psi, which is defined as minus infinity to infinity psi of t square dt, that is equal to 1, which means that we have unit energy mother wavelet. And the third is that it is centered around, not necessarily exactly at t, but it is centered around t equal to 0. The most important property in here is this zero mean property. Unit energy, that's not so special about the wavelets. And centered around t equal to 0, you can move it a little bit here and there. That's just a shift. That's not that critical. Okay. So once you are given the mother wavelet, you basically generate all possible functions that you will be dealing with. So you construct scalings and translations of the mother wavelet to generate a wavelet dictionary. So the dictionary is given by the function phi psi of u comma st, okay, which simply means that you take your mother wavelet and first of all you shift it by time u, okay, so you shift it in time. Since the mother wavelet is localized in time, previously if it was localized around 0, now it's localized around u, okay. But you just don't shift it, you also scale the wavelet by a factor of s, okay. And we want all of these to be also unit energy, so because of that we have to have 1 over square root of s in there. So u of course can be positive or negative, and the scale parameter is only positive. So what is happening, you are taking your mother wavelet and you are, first of all, for every possible scale, every positive scale, you are first of all scaling your mother wavelet in size. You are either contracting it or expanding it. If the scale s is number 1, if s is greater than 1, then what does that mean? If s is greater than 1, then you are expanding your mother wavelet, right? So you are expanding in time. And if s is less than 1, then you are contracting in time. So an example will be, if I take the look at the Haar wavelet and my s is equal to 2, then I, instead of going from minus 1/2 to 1/2, it will be now going from minus 1 to 1. Okay. So 1, so it will be expanded, and because we still want it to have unit energy, the height will be 1 over square root of 2 minus 1 over square root of 2. Okay. Minus 1 plus 1. So this is for the case of s equal to 2, the Haar wavelet, and u equal to 0. Similarly, I can contract it by using, say, using s equal to 1/2. If I do s equal to 1/2, then I get this will become minus 1/4 and 1/4. Okay. And the height will become square root of 2 and square root of 2. Minus square root of 2. Okay. So the idea is that you take your mother wavelet and you scale it at different scales. Scaling means you either are going to contract it or expand it. And then for every given scale, you shift it in time. Okay. Now, the time shift is easier to see what that is doing. As you shift it in time, now you have localization around u. So if you somehow use that mother wavelet for analysis, we'll give a formal expression of the wavelet transform. But if you use that mother wavelet, that version of the mother wavelet, or that time-shifted version, you are now doing analysis which is localized around that time period. So let's say u equals to 20, your wavelet has moved to time 20, and since it's localized in time, it has certain just small support, you are effectively analyzing that portion of your signal. So that's the time localization property of the wavelet. Okay, we'll look at it more formally. But getting a handle on the scale is a little bit tricky, which we'll try to understand. And the other property, the zero mean property, actually also gives the wavelets a characteristic that we need to understand. So we'll now try to understand both of them together. The first part is, let's look at the fact that the mother wavelet is zero mean. Now, this mother wavelet has a Fourier transform. So psi of t has a Fourier transform, psi of j omega. Okay. We know that the mean of this mother wavelet is 0. What do we know about the Fourier transform of this mother wavelet? This means that at omega equal to 0, the Fourier transform of the mother wavelet is 0. So because of the fact the Fourier transform of any mother wavelet, just by the token that it's zero mean, has to have this nature that around 0 it is 0. Okay, so all Fourier transforms of mother wavelets will look like the shape that I showed earlier for the Mexican hat. They won't have any mass in frequency around 0 because of the very fact that the mean of this is 0. Okay, so you can have Fourier transform like these. And the shape of these will vary, but they will not be concentrated around 0. Okay, so let's call the center of this thing as omega naught and minus omega naught. So you can think of it that this mother wavelet has a Fourier transform which is localized around, if I talk about only positive frequencies, it's localized around omega naught, where omega naught is away from 0. So effectively, I can think of this psi of t, and it will become clear why I want to think of it like that. I can relate it to an impulse response of a bandpass filter. Now, if psi of t has this property, let's take a look at what does scaling do to this center of this frequency. Okay, what we are after is, or what we want to argue is that the time shifts give the wavelets this property of localized in time analysis. If I have a wavelet shifted in certain time, it helps me analyze my signal around that time. What I want to argue is that my scale gives me the ability to do analysis which is localized in frequency. And I want to relate the scale of my mother wavelet to the frequency where that wavelet is concentrated at. Okay? So in general, we know the relationship between time scales and frequencies. We have a simple duality expression. If you contract a signal in time, it expands in frequency. If you expand a signal in time, it contracts in frequency. So that is just a simple duality relationship. But because of the fact that we are dealing with these mother wavelets which have this bandpass nature, it's effectively going to move where these wavelets are localized in frequency. Okay. So if you remember, let's look at psi of t over s. If we just want to take a look at the Fourier transform of this thing, what is that in relation to the Fourier transform of psi? It's just the duality property. It will be s times psi of j s omega. Okay. So if I want to ask what is the Fourier transform of psi ust, which is shifted, which is equal to psi 1 over square root of s psi of t minus u over s. Okay. What is the Fourier transform of that thing? Well, s times square root divided by square root of s, that's square root of s. What is this u going to do? That is going to just introduce a phase shift. So I get e to the minus j u omega, and because of the scale, I get psi of j s omega. So let's just look at the amplitude of the Fourier transform of this thing. So if I look at the amplitude of the Fourier transform of this, that is simply square root of s times psi of j s omega absolute value. Okay. So let's then try to understand what happens as we change our scale. As s changes, what is happening to the Fourier transform of psi us? Okay, I'm going to fix u because we already understand what u does. That helps us do local analysis in time. Now what I'm interested in is, as I change s, how does the Fourier transform of the mother wavelet, which always have this sort of a shape, how does that change as I change my s? So let's first look at the case of s less than 1. Okay, and actually look at s much smaller than 1. Well, in that case, what is going to happen? My Fourier transform of this psi ust is going to expand, and if I look at the magnitude here, which is square root of s psi of j s omega absolute value, this omega naught will move to omega naught over s, which will be bigger than omega naught because s is much smaller. You're dividing by a very small number, so omega naught divided by s is going to be a much bigger number than omega naught. So if s is much smaller than 1, then actually my omega naught sits somewhere here, but my omega naught over s is going to be somewhere here. Okay. Similarly, my minus omega naught is going to be here, but my minus omega naught over s is going to be here. And you will have a Fourier transform centered around omega naught over s, but that whole Fourier transform now will also be spread out. So you will have a hump which will be more spread out. And the height of this thing compared to the previous case, let's say if it was unity, just as an example, that will be square root of s, which will be a very small number because s is very small. So when s is very small, much smaller than 1, what does phi ust does? That scaled version of my mother wavelet is effectively analyzing very high frequencies, and the localization around that high frequency is actually pretty bad, right? It's spread out. So at high frequencies, this wavelet function is going to, for small scale, that wavelet function is effectively providing you some information about high frequencies. And the resolution at very high frequencies, the higher you go, the worse your resolution will be. Okay. So if you remember the picture that we saw in class yesterday, we saw that higher the frequency, your blocks sort of are in frequency, they get elongated. Your resolution is getting bad. Okay. But what does scale as much smaller than 1 mean in terms of time? If I was talking about, for example, Haar, so if I take the example of Haar, this thing, my endpoint, so this is Haar, okay, and this endpoint, instead of 1/2, it will be s over 2, and this will be minus s over 2, which is much smaller than 1/2. So what has happened? As my scale has become very small, as my scale has gone close to 0, what is happening in the time domain? In the time domain, my function is becoming more and more localized. It's getting shrunk, contracted. As I take s closer to 0, it's almost becoming just like one single up and down. Okay? So I am now getting, as I shrink my scale, I am getting very high time resolution because I'm looking at a really small region. Okay? And for that region, I am looking at high frequencies. So very small scale, very high time resolution, and analysis of high frequencies. But the moment you go into high frequencies, your resolution in frequency is getting bad. Okay? So for small scale and s much smaller than 1, we have that psi ust is highly localized in time, and the more you are localized, the higher is your resolution. So it's highly localized in time, but it is concentrated around high frequencies and not that well localized in frequency. Okay. So this scaling is sort of killing two birds with one stone. It's giving you, it's not only taking your signal to high frequency, but it's also increasing your time resolution. Now let's take a look at the example of let's look at S much bigger than 1. And let's ask what happens then. So in frequency, I'm going to work with the same picture. I have originally my mother wavelet was concentrated around omega naught and minus omega naught. But now since S is much bigger, omega naught over S is much smaller than omega naught. So I am now, the scaling is still omega naught over S and minus omega naught over S. But now omega naught over S has to be smaller than omega naught. Okay. And what is going to be the extent of that scaling? So previously it had expanded this hump around omega naught because S was very small. Now it's going to contract that hump. So this thing is now going to be contracted around this thing, around minus omega naught, and the height of that will be square root of S, of course, but that, since S is large, this height is high. So what has happened as your scale has increased? You have, first of all, moved to smaller frequencies, and you have become highly localized in frequency. So effectively, your resolution in frequency has increased. Okay. But what has happened in time? So this was square root of S psi of Js omega absolute value. What has happened in time? Again, take the example of the Haar. Instead of ending at 1 by 2, you are ending at S by 2, which is a really large number. So you go from minus S by 2 to S by 2. Okay. And of course, the height of this thing is 1 over square root of S and minus 1 over square root of S. So that is a small number. So you have 1/2 and minus 1/2 and 1/2 here. So as your scale has gone up, you have actually expanded your signal in time, which means your time resolution has now become worsened. Okay. Right now, I'm just talking about the properties of these time shifts and scaled versions of your mother wavelet. We haven't defined the wavelet transform per se, but that should itself give you a sense of where we are going with it. Effectively, each of these time and scale shifted versions is going to do some local time analysis and local frequency analysis. All wavelets that are at a small scale are going to do very good job of local time analysis, and at the same time they will be doing high frequency analysis, but the localization in frequency will be high. Okay. And all wavelets at large scales will be doing bad job of localization in time, so their time analysis won't have very good resolution, but their frequency analysis will have really good resolution. Okay. Now, I want to also point out that if you want to get closer and closer to low frequencies, okay, in the limit as S goes to infinity, your omega naught over S goes to 0. But in general, as S keeps on becoming larger and larger, you keep on shifting closer and closer to 0, but in reality, you never hit 0. Okay, so you need an infinite collection of these time and scales, these time and scale versions of your original mother wavelet to be able to cover all frequencies. Okay, you should really think of these phi USTs as the as bandpass filters, and the smaller, for S very large, your bandpass filters are getting close to zero, but they are never hitting zero because their bandwidth is now shrinking. As you get closer to smaller frequencies, your bandwidth is shrinking. Okay, and we'll get back to that concept later when we define something called the scaling function. So in wavelets, there are two main things. There is this mother wavelet. All time and frequency and scales of that give you the wavelet transform, but in general, you need too many of them. So you actually say, I'm going to stop at a certain scale, and after that, I just want to use a collective approximation. And for that, we need something called the scaling function. Okay. So what's the formal definition of a wavelet transform? Let's start with that. Wavelet transform is given by simple inner products of your function with these time shifted and scaled versions of your mother wavelet. Okay. So wavelet transform, it's a function of two variables. Just like the short time Fourier transform, so it has one variable is u, which is time shift, and the other is scale s. Okay, so I'm going to write that as capital X U S. So u for time shift, s for the scale, and that is simply given by the inner product between one of this right scaled version and shifted version. So that is simply x, inner product of x, and psi us. Okay, where the inner product is defined on L2R. So we have done what is the inner product on L2R defined. That's just the integral minus infinity to infinity x of t 1 over square root of s psi conjugate of t minus u over s dt. So, and that's pretty much how every transform that we have studied is effectively defined. It's defined as an inner product between the function or the signal that you are interested in and the functions through which you want to represent your original signal. So for the discrete time Fourier transform or continuous time Fourier transform, these are just the exponentials or cosines and sines. And the inner product, if you go to continuous time, then it's defined this way. If you go to discrete time, then it's defined through the summation. But the general principle is always the same. Okay? You are simply computing the coefficients. So these inner products, or XUS, this is called the wavelet transform coefficient. At u comma s, just like the discrete time Fourier transform coefficients. Now, long time ago, we had also talked about how an inner product in L2R can be simply expressed as basically convolution with a filter followed by a sampling operation. So we can do that here again. X of US, if I simply do the right change of right manipulation, it's 1 over square root of S psi conjugate. I do minus U minus T over S dt. So now this is exactly in terms of the convolution expression. XUS is nothing but convolving X with the function, let's define it as psi bar of S of t. So I define that as 1 over square root of S psi conjugate of minus t over S. If I define psi bar S of t like this, then this inner product is nothing but convolution of X. This is just a convolution formula, X of t, U minus t, where the independent variable is U. So this is just a convolution of X with psi bar of S. And once you compute the convolution, you just take the value at time U. We have done that when we talked about abstract notions of sampling earlier in very start of this class. So what this means is that I can actually XUS can be simply computed by taking my X of t and passing it through a filter where the filter is this psi bar S of t. Okay. And then at the output, I take the sample at t equal to U, and it will give me X of US. Okay. So a Fourier, a wavelet coefficient at time U and scale S is simply given by a filtering operation. You filter, and then you sample at t equal to U. And what is the Fourier transform of this filter? So the Fourier transform of psi bar S of t, that's simply 1 over square root of S, Fourier transform of psi conjugate minus t over S. Okay. And that is simply equal to 1 over square root of S. If you remember the properties, one we have already done. Because of this scale, I just get a factor of S outside, and I get psi of JS omega. Okay? And because of the conjugate and minus t, I get a conjugate operation here. In general, what is this saying? That the frequency response of this filter, if you look at the magnitude, psi bar j omega, absolute value, the response of that filter is exactly what we have talked about. That is simply square root of S psi of j omega, absolute value, S j omega. Effectively, it's a band pass filter, because we have already done this, right? We already computed what does this filter mean. Square root of S psi of JS omega. So the wavelet coefficient at scale S for every time shift. The wavelet coefficient at scale S is nothing but filtering your signal through a bandpass filter, where the bandpass filter's Fourier transform is given by this expression. And what is this expression? This means that the bandpass filter is situated at omega naught over S. So if scale is very small, the bandpass filter is centered around very high frequencies. If the scale is very high, it is centered around low frequencies. Okay? But that is all that it is doing. It is helping you figure out what is the frequency of your signal around that region. It's just throwing away all the frequencies except frequencies in that region. Okay? So scaled coefficients related to certain scale are telling you information about frequencies that are centered around omega naught over S. And that is true for all of the other scale coefficients. Now in this setting, since this is a continuous wavelet transform, you need infinite amount of these filters because they are infinite scales to do that. But the general principle, whether you're talking about continuous wavelet transform or the discrete wavelet transform, is effectively the same thing. So this XUS define the wavelet transform coefficients for us. The question is, how do we compute the inverse transform? So let's look at the expression for that. So we'll define a constant C of psi, which is equal to 0 to infinity psi of j omega square divided by omega d omega. Okay. And then the inverse wavelet transform is defined as 1 over c psi. So since your wavelet transform is two-dimensional, you do need to do integration over both the scale. So this first integration is for the scale. The second integration is for the time shifts. You take your wavelet transform coefficients and you simply multiply them with your wavelet, different time and scale shifted wavelets. So T minus U over S. du ds over S squared. Okay. Now, it is important for you to remember that in general, just like the short time Fourier transform, continuous wavelet transform is not an orthogonal transform. And that should be at some level pretty easy to see if you just shift one wavelet by a small amount from other. Unless you really have a good relationship between the two, if you look at it for all possible values of u, they are not going to be orthogonal to each other if you carry out their inner products. Okay. Now, this is all true. Let's for the case where we are willing to use an infinite number of scales. We start from s almost equal to 0 and we go s equal to infinity. Now in general, what we do is after a while, so remember, as we start from s equal to 0, we are starting at very high frequency. Omega naught over s is infinity. Then you start with scale s equal to 0. As you keep on increasing the scale, you are coming down and down to lower frequencies. Okay. Now, at some point, you say that that is enough, and you want to stop at some frequency s equal to s naught. So you stop at some frequency s equal to s naught, and you have now covered all the frequencies, all of your wavelets have covered frequencies from omega equal to infinity to omega equal to omega naught over s. But there are still some frequencies left from omega naught over s to 0 that have been uncovered. So if you want to not use all possible scales, if you want to stop at omega naught over s, you need some sort of a correction term to cover all the frequencies that are left. So say we stop at scale s equal to s naught. So we started with s equal to 0 and we have gone up to s naught. Okay. As we started with s equal to 0, we had started our band from almost omega equal to infinity, and now we have finally stopped at omega naught over s naught and minus omega naught over s naught. Okay. And based upon the value of this s naught, we'll have some spread. And other values of s which were smaller than s naught gave us, for example, things like this. We kept on getting bigger and bigger bands. They should actually be going down too, so the height of them should be going down, right? And so forth. So all of these, and the same is true for negative frequencies. I'm not drawing them here, but this is, so we have covered all the frequencies up to omega naught over s naught. But there is this region that is left uncovered. Right? And we now somehow need information about our signal to fill in this piece of information. Because a time domain signal, it consists of all these frequencies. Using all the bandpass filters, we have learned about all the frequencies. Now we are left with these low pass frequencies. And to take care of this gap, we can use something which is called the scaling function. The scaling function in wavelet analysis helps us understand about all the low pass frequencies in the signal. Okay. In general, it is usually in the literature written as phi of t. In some cases, you will actually find literature which confuse the two, the scaling function and the mother wavelet. They are two distinct things. They are related to each other, but they are not the same thing. Okay? So don't make the mistake of calling the scaling function as the mother wavelet. Now, what is the relationship of the scaling function to the mother wavelet? It's defined as phi j of omega, any function whose magnitude squared of the Fourier transform is equal to this phi of js omega absolute squared ds over s. Okay. So any function which has this magnitude squared, now in general, the magnitude is not alone sufficient to describe a function, but in this case, all we care about is this magnitude, and we can take any phase information. We can assign any arbitrary phase to this scaling function. It won't change anything. Okay. So the way to understand is that the scaling function looks at the total, captures the total energy in all wavelets above scale s equal to 1. Okay. You can further simplify that through a simple change of variable, and you can get omega infinity psi of j theta absolute squared d zeta over theta. And as I said earlier, pick any phase for this. So for example, for the Haar wavelet, the scaling function is just a constant. The scaling function for a Haar wavelet is just minus 1/2 to 1/2. Okay. Now, let's look at the case that how can we then how do we compute all the information about our signal using scales up to S0 and then using the scaling function. And then we can also invert our wavelet transform using wavelet transforms up to that scale and the scaling function approximation. Okay. But first, some properties. Number one is you can check that if you apply that, the energy in my, so it's also a unit energy function. Okay. The other thing to note is the following. If you look at omega going to 0, phi of j omega absolute squared, then that is equal to C of psi, okay, which we define for the inverse wavelet transform, which is not equal to 0. So what this is saying is that the scaling function, if you look at the Fourier transform of the scaling function, at omega equal to 0, it is non-zero. What would that make the scaling function? It will make it a low-pass filter. Okay? So it's completely in keeping with the understanding that we had that we need something which is able to cover all the low frequencies that have not been covered by the scales up to S0. So we needed a low-pass filter, and scaling function, indeed, its Fourier transform looks like a low-pass filter. Okay. In particular, if you look at the scaling function of this Haar wavelet, we know what it is, right? It is a low-pass filter. It has a sink shape. Right? So because of its low-pass nature, it captures all the low energy, and we can capture that through, you can call it the approximation, low frequency approximation, which is given by L of x us. It is given by minus infinity to infinity x of t 1 over square root of s phi of t minus u over s dt. Okay. So it's given in the similar fashion. The low frequency approximations are given in the similar fashion as the wavelet transform. Okay. But what happens is that instead of requiring the low frequency approximations for all scale, you basically stop your wavelet transform at certain scale, and then you compute the low frequency approximation at that particular scale, and that is enough. You don't have to compute any more scales. Okay. So the idea is that you can compute this. So you can compute. Now another way of computing the wavelet transform will be using both the mother wavelet and the scaling function. It will be that you first pick some scale up to which you want to compute the original wavelet coefficients. So then you, number one, compute x of us for all u and for all s between s and s naught. Okay. So previously we were going for the scales up to infinity. Now we will stop at s naught. And then to take care of the remaining pieces, to take care of the remaining low frequency component, we compute Lx of us naught, okay, for all u. So for the mother wavelet, we have to compute all possible scales up to s naught. But for the scaling function, now we only compute at the scale where we end our wavelet, the computation of our wavelet coefficients. Okay, and these will capture high frequencies, where high is a relative term. It could go up to pretty low, but it would not be around the vicinity of 0. So capture high frequencies, and this will capture the remaining low frequencies. Now, if you want to compute the inverse continuous wavelet transform in that case, then again it will have two terms. The first will be exactly what we had before, but instead of the scale integral going from 0 to infinity, it will go from 0 to s naught. And then for minus infinity to infinity, x of us, 1 over square root of s, psi of t minus u over s, du ds over s square. So this will take care of the reconstruction due to x us, but we also need to take care of the reconstruction due to the low pass component that is left, and that is given by 1 over c psi s naught minus infinity to infinity Lx of us naught, 1 over square root of s naught, phi of t minus u over s naught du. And of course, as s naught goes to infinity, then this second term will go to 0. Right? Now, we have already talked about the case of the wavelet coefficients being given by the filtering operation. We are filtering with a band pass filter. I just want to show that this is also the same thing. If you look at it, it's again the case that we have minus infinity to infinity x of t psi of minus u minus t over s times 1 over square root of s dt. Okay, so indeed, computing this low-pass approximation at any given scale using the scaling function is also simply given by a filtering of x with this psi of minus t over s. So let's define a function like before, psi bar of st as equal to 1 over square root of s psi of minus t over s. Okay. Then it's easy to see that this is just convolution of x with the psi bar of s computed at time t equal to u. Okay. So the general, if you want to talk about how to just a conceptual understanding of what the Fourier transform of what is the Fourier transform going to look, what is the continuous wavelet transform going to look like? What you have is x of t, and you are filtering it with different scales. So you perhaps start with one function which is very small. Let's say you have some number epsilon which is very small, and you do psi of minus t over epsilon. So you have this filter, and then you sample it at t equal to u, and you get x of u epsilon. So for different values of u, you are looking at really high frequencies, and you keep on increasing it till you come very close to S naught. So here I'm defining epsilon is a very small number. And then you get to S naught, and you stop before S naught, so you have S naught minus epsilon psi of minus t over S naught minus epsilon. And again, you just sample at t equal to u, and you get x of u S naught minus epsilon. And in between, you are getting all the other scales. And at S naught, you stop, and the final thing is you have the low-pass filter. At the very end, after you have stopped calculating your different scale, you have the low-pass filter, which effectively involves filtering with the scaling function minus t over S naught. And you get Lx of u S naught. Okay. And all of these things together, for different values of u, they are giving you different time regions. They are giving you the time information and different scales. This is the highest frequency, and this is the lowest frequency. So as you go from here to here, you are going down from high to low frequencies. Okay. And of course, you are not going to be able to compute this explicitly like this, because it is a continuous wavelet transform, and you need infinite amount of scales. But the general idea, whether you go to the discrete wavelet transform or stay with that, is more or less along the same lines. So in the next class, we'll talk about how you can compute the discrete wavelet transform, which is simply at some level just sampling of these mother wavelets and the scaling functions.